Here I have tried to create a model of a mini gas chromatography. We have the major components, the injection port, the column, and the detector. We'll start off with the injection port. The sample is first injected through the injection port. The volume of the sample injected is very small. Once the sample enters the injection port, it will be brought into the gas phase because the injection port is held at a very high temperature. The injection port in this particular gas chromatography uses a split injection method. This is the most common method. It delivers a small percentage of the sample injected into the column of about 0.2 to 2% of the sample. Notice that the sample injected has a very small volume to begin with, and through the split injection method, only a very small percentage of the very small volume goes into the column. This is done by having a split point that shuttles most of the sample away from the column. There is also something known as the split ratio, which is basically the amount of sample that does not reach the column versus the sample that does reach the column. Next is the column. The column is contained in an oven and is held at an elevated temperature which maintains the sample in the gas phase as it goes through the column. Here the separation is occurring in this equilibrium between the gas phase and the stationary phase. The stationary phase is the very long capillary tube that is coiled in a ring. The capillary tube is very thin, which allows the most interaction between the walls of the capillary tube and the sample molecules. The polarity of the capillary tube can be changed by changing what the walls of the capillary tube is coated with, whether it is coated with hydrophobic or hydrophilic molecules. The polarity of the walls of the capillary tube determines how the sample molecules is effectively separated. In addition to separating the sample molecules based on their polarity, the molecules are also separated based on their boiling points. As expected, molecules that have higher boiling points will come off later in the gas chromatography. To improve resolution, we can also do something called as temperature programming, in which we start at a low temperature to allow molecules with a lower boiling point to travel through the column and interact with the stationary phase. Then we can raise the temperature over time to kick off the molecules that have a higher boiling point. Say we have a sample that consists of methanol, ethanol, and butanol. Since the stationary phase in this particular gas chromatography is polar, and all of the compounds in the sample are also polar because they're all alcohols, the dilution order will be based on their boiling point. Thus, the dilution order would be methanol, ethanol, finally butanol. Finally is the detector. The detector used in this particular gas chromatography is a flame ionization detector. As the name suggests, it involves a flame. The flame is maintained by hydrogen gas and air. As the sample molecules enter the detector, the molecules will burn up and generate ions. This will change the temperature of the flame. The change in temperature of the flame is based on how much of the molecules is passing at any given time. The change in temperature will change the intensity of the voltage that is read on the electrode. This will create a current and generate a signal. The pros of the flame ionization detector are it's relatively cheap to acquire and operate, requires low maintenance, sensitive for organic molecules, has high detectability, and has a wide dynamic range. The cons of the flame ionization detector are it cannot be used to detect inorganic molecules, and it destroys the sample during the combustion step.